Guys, welcome. Yeah, so example 0 here, and as with all example zeros, we're going to try to figure out how and why the Gram-Schmidt process works. And in examples 1 through 3, so 4 total examples, but yeah, in examples 1 through 3, you'll get to see practice problems. In example 1, we work with 3 vectors in R3, and in example 2, we work with an inner product defined on vectors with complex entries, and in example 3, we work with an inner product defined on polynomials. So plenty of variety to come, but yeah, let's figure out how this process works. Yeah, and that's this video. Okay, so big picture, here's what we're doing. So we start with a set of n linearly independent vectors, and let's call those the W vectors. And then we use the Gram-Schmidt process, so the formulas involved are here, and turn these W vectors into the V vectors. And so by the time we get to the V vectors, so by the time we've used the Gram-Schmidt process, we've made mutually perpendicular vectors. So these V vectors are mutually orthogonal. And then we divide these V vectors by their respective magnitude or norm and turn them into unit vectors. Yeah, okay, so that's that. And notice that the span of S is the same as the span of S prime, which is the same as the span of S double prime, and also that the U vectors clearly are mutually orthogonal, just like the V vectors. And here's how we get to the U vectors from the V vectors, so it's pretty straightforward. Now, the big picture, or the big formula rather, is right here for finding the V vectors from the W vectors. But yeah, this formula starts with first setting V1 equal to W1, and applied to the case of V2, it would look like this, and then V3 it would look like this, and clearly V4 would have like one vector over here being subtracted, right? So it quickly gets more tedious and more difficult to find like values of V sub k for large K, and so it's only reasonable to ask you to find V2 and V3 in your classroom or in the examples to come. Yeah? Okay, cool. Otherwise, let's not delay and get started with understanding using visuals how this process works. Now, what I'm going to do is I'm going to demonstrate how this construction does in fact make V1 and V2 perpendicular, and I'm going to use visuals to explain how V1 and V2 are made perpendicular. Yeah? Okay, cool. Now, so if you want to see it for the three vectors V1, V2, and V3, I'm saying use an extension of the idea and the discussion that is about to come, and then like you'll be able to see it for V3 also, and that is how V3 is also made perpendicular to V1 and V2. But for now, we're just gonna focus on how V1 and V2 are made perpendicular. To do that, let's break down the formula for V2. So the formula for V2 says that V2 is equal to W2, it's equal to I don't like that W, it's equal to W2, and then minus, right, and let's pause here for a sec, minus, in a video I've already made, I show that the inner product between W2 and V1, this here would have to equal the norm of W2, that's the length of W2, times the norm of V1 times cosine of theta. I've already made a video proving this, and I'll try to link that video below this video. But yeah, the point is that this here is equal to this. And notice that this here is a scalar. It's just some number. Yeah? Okay, cool. Alright, so I'm going to choose to write this here in this form. And yeah, obviously I've also abandoned my color coding, but we'll live. So W2 norm, and then times norm of V1, and then times cosine theta, where theta is the angle between the vectors V1 and W2. Okay, now this here is this here, but it has a denominator, and that's the norm of V1 squared. And so I'm going to write the norm of V1 squared. as norm of v1 times the norm of v1, but the other norm of v1 I'm going to intentionally write over here, and then obviously what I have left to write is this v1 here, which is that guy. Yeah, okay, cool. Now notice that if you want, I could put a break and like indicate multiplication right there, but it's pretty clear that this here is just v1 made a unit vector, right? Okay, cool. So technically it's like u1, but it's v1 made a unit vector. Okay, got it. Otherwise, in these parts, I can cancel this and this. Yeah, okay, cool. So that says then that v2 is equal to w2 minus the norm of w2. Oh my god, Jesus, I'm having a bad handwriting day. Sorry guys. The norm of w2 times cosine theta, and then we just have and I'll write it like color coded, I suppose, v1 over the norm of v1, right? Okay, cool. And now it's time to go to our visual. I did promise that I was going to use visuals to help in our discussion here. So let me keep to my promise. There's that bad syntax. Let me keep my promise. Okay, whatever. All right. So we know that the vectors w1 and w2 aren't necessarily perpendicular to start. In fact, our job is to make them perpendicular by turning them into the v vectors. So let's say that w1 was this long and it was in that direction, and then w2 is this long and in this direction. Yeah, clearly I've made w2 shorter than w1, but it could be the other way, and the angle between them could be bigger or whatever, but they didn't start off perpendicular. That's the point. Okay, cool. Now the process starts by making v1 equal to w1, right? And first let me write that this is w1 and this is w2, and so the process starts by making v1 equal to w1. Fine. Okay, so here is v1, right? Okay, so this is equal to v1. Got it. And then it says that the way we make v2 is using this here. But what is this nonsense here? Well, first, what is this fella here? This guy here, right? The norm of w2, so the length of the vector w2 times the cosine of theta is a scalar projection of w2 onto w1. What? Basically, it is the length of the shadow of the vector w2. So basically, here's what I'm saying. If you take this vector w2 and from it drop a perpendicular to, let me make sure that I'm 90 degrees, I am. Okay, drop a perpendicular to the vector w1, then this length here, this distance from here to here, the distance from here to here, is equal to this guy. That's what this guy equals. Okay, cool. I get it. So the length of this, the distance right here, but this here is not a vector, notice. It's just a number, so it just represents this length. Got it. And then we have this quantity here, which we haven't talked about. Notice that the length from here to here is the length of v1 or w1, as they are equal. But this quantity here is v1 made a unit vector. So assuming that this length here is more than 1, the length of v1, and therefore the length of w1 to start with, assuming that it was longer than 1, more than 1, then we would say that the quantity the quantity v1 divided by the norm of v1 could look like this. And it's not a quantity, it's a vector, right? Okay, but yeah, the vector v1 divided by the norm of v1, which is like basically the vector v1 made a unit vector, could look like this if we agree that this red length here is length of 1, and it's not like perfectly aligned, so like let me get that better. Okay, but yeah, if we agree that this red line is of length 1 here, then this here, this vector in red that I just drew, could be v1 divided by the norm of v1. Let's assume it is, yeah? And that's to say that v1 to start with was longer than 1, the vector v1. Yeah, okay. Anyway, this is what we just said. Okay, so this here, the red vector, is this. And then the distance from here to here is the quantity that. The value of this number is the distance from here to here. So what happens when we multiply this red vector by this number here, the length from here to here, whatever number that is. And notice that number could be like 3/4. It could be something more interesting, but it could be 3/4. Well, if we did 3/4 times this unit vector, what's going to happen? This unit vector is going to shrink down to a size of 3/4. In other words, this whole thing here, right? This whole thing here, including the norm of W2 times cosine theta times V1 over the norm of V1, all of that is going to be this here. It's going to be this here. It's going to be this vector right there. Yeah? Okay. Got it. And what are we doing with this vector here? So let's call it like, I don't even know what we'd call it. W, U, no, I've used U, V, and then X, I guess. So let's call this X vector. So if this is the X vector right here, and it's equal to all of that, what we're doing is we're subtracting X from W2. Well, notice that negative X would be this here. So since this here is negative X, it's the negative X vector, this here, and this here is W2. If we have W2 plus negative X, that's the same thing as W2 minus X. And so W2 plus the negative X, which is W2 minus X, would be this here. It would be this here. It would be this here. If you know, like, simple basic vector addition, you'd know that the way we just constructed stuff, this here is equal to V2. In other words, what I just drew is the vector that is equal to W2 minus X. That's W2 plus a negative X. That's this vector here. Well, this vector, drawing it there, is the same thing as like drawing it out here. And in our visual, it's of this length, but had W2 been very long, notice that V2 would have been very long as well. So my visual is like only one possible visual of what could have happened, but yeah. So anyway, here's what I'm saying. So we had V1, which was equal to W1, and we just found a V2 so that it is perpendicular to V1. So here it is. Yeah, okay, let's draw this separately. Now, so here's what just happened. So we just figured out that this is like V2, and to start, we had V1, which was equal to W1, and so this was V1, which is equal to W1, and this is V2, and it's perpendicular to it. So V1 and V2 are orthogonal, and then we shrink them down so that they're of unit length by the time we get to the U vectors. And so that just means that when we're done with the process and we get to the U vectors, our visual will look more like this, which is like that, and then assuming that what I just drew is of length 1, and then this, which is supposed to be also of length 1. Yeah? Okay, cool. Alright, I hope you enjoyed this, and yeah. And what is it? Of course, if you wanted V3, so what your construction, what it would do is like kind of like the XYZ coordinate axes. It would make it so that by the time you get to U3, U3 is also of length 1 and mutually perpendicular to both of these guys. Yeah? Okay, cool. All right, I'm done. Keep watching, and examples 1, 2, and 3 to come will offer a lot. Yeah? All right, bye.